Okay, everyone, I'm going to get started for our next session. We're going to take a look at non-uniform sampling, and I'll walk you through a tutorial here. So let's start off with the real VNC viewer. You should each have that installed on your local machines, and you can open up a session to NMR Box. If you don't have a bookmarked session, as Mark walked you all through this morning, you can type your username.nmrbox.org into that title bar at the top, and then it'll prompt you for your username and password and open up a session for you. This is a local copy of the tutorial that I'm going to walk everyone through. This has also been deposited inside NMR Box. So if you go into your home folder on NMR Box, there should be a folder in there called Summer Workshop 2020. And these are the names of all the presenters that'll participate throughout the summer. And as any of those presenters have files or things to share with you, they can put it into these folders and it'll sync to your account. So if you go into my folder for Schuyler, you'll see a PDF in here. And if you open that up, you'll get the same copy of this version I'm showing on screen. So that way you can have a local copy open if you want to look at that or refer back to it. Otherwise, I'm going to leave this copy in the shared view so everybody can see this as well. I'll give everyone just a minute or so to get that set up. And if anyone has any questions or difficulties in connecting to NMR Box or getting things configured like this, go ahead and raise your hand and we'll spend a minute or two troubleshooting. Otherwise, I can work along with the tutorial and people can follow that on my screen, but I'll give everyone just a second here. Okay, so we'll continue on then. So here's the tutorial guide. This will be a tutorial of non-uniform sampling using a software program I've put together called NUSTool. This is something that came into being as a way to support some of our earlier workshops and some of our in-house research objectives. It's grown in its capabilities, and over this past year went through kind of a rebuild, a refactor to support a lot of new features and hopefully position it to be modular and easily developed going into the future. So this is the first time we're doing a walkthrough with this version of the tutorial. If you do find any glitches, bugs, or anything else, that shared box note that we all have access to, feel free to kind of mark your experience on there, note any bugs that you might find. So what is NUSTool? This is going to be a software package that helps with sample schedule generation. We can write these sample schedules to files, so that way you can use them to run NUS experiments. You can load sample schedules from file into this tool, so that way you can plot, visualize them, and you can use some analysis tools in here to take a look at the quality of those sample schedules. There are a couple of ways you can access NUSTool. So on NMR Box, you can open up your terminal. And in the terminal, simply type NUS-TOOL, and you can use tab to autocomplete that as you go. And by default, that is going to run and open up the GUI for the program. I'll give everyone a second just to get that open. While people are doing that, I'll also note that what we just typed, NUS-tool, is actually a wrapper for the program. And as Mark showed this morning, inside user software, we have all the software programs for NMR Box installed. And in the subfolder user software bin, that's where we stash a bunch of wrappers to the enormous number of executables and binaries that might be of interest to our user community. In addition, NUSTool is a Python package. So if you do any Python coding on your own, you can access the source code on NMR Box. You could import NUSTool as a module into your own code and directly access functions that are built into NUSTool. And while you use NUSTool in this GUI form here, as you'll see in a little bit, you can also have NUSTool print for you the equivalent command that you can then run at the command line. So something you could run in the terminal or in your own scripts. So the idea is that you can use the graphical user interface here of NUSTool to build your sample schedules, get an understanding for the different schemes that are available to you. And then if you wanted to put that into some kind of script or survey analysis, you can get the equivalent command line syntax and use that. So here we are now on page 2. Everybody has launched NUSTool. This is the basic window that shows up. I've got a couple notes here at the top. If you're having any resolution issues or questions, you can always resize your virtual desktop, as Mark showed this morning with the resolution changer. In addition, inside of NUSTool, if you go over to the settings tab, there are a number of different ways for you in here to control the font size that you see in the GUI. So maybe for now, I'll bump my font size up just a little bit to make it a little larger on screen for you. Although it is going to clip some of those labels on the edge, but I think we'll be fine with that. So the layout of NUSTool is that on the left-hand side of this, we have input, and on the right-hand side, we've got output. So on our input panel over here, these tabs at the top control the basic functions that you can use NUSTool for: generating sample schedules, writing, loading, analyzing, in the settings panel we just looked at. And then when you select one of these functions, you simply work yourself down the page. And depending upon what you're doing, when you're generating a sample schedule, as you make selections and change parameters, you'll see changes lower down in the form that reflect the options that are now available to you. And then typically at the bottom of one of these panels are some action buttons to perform some task. So in this case, you could fill in parameters for a sample schedule, then generate one. On the right-hand side, this is where you get output. In the top, you'll see output to the command line. So on the Out tab, you'll see standard output. And if there are any errors or other error checking things running in the background, you'll be brought over to this error panel and it'll show you potentially a missing input parameter or something else not working correctly. You've got a clear button down here at the bottom to clear the contents of this if you want a fresh screen. If you click on the About button, you'll see people involved in developing this program, as well as the contributions made by sample schedule developers. So we've got Quantile Sampling in here from David Rodniak and company, and Poisson Gap Sampling from Sven Hibberts. And I can clear that window. If you click on Help, you'll get a very short tutorial kind of guide in here about how to use NUSTool. I think the PDF I'm sharing with you right now is far more comprehensive, but if you ever need a quick reference, this is at least built in so you can take a look. You'll also notice that I just use this little handle in here where you can drag a slider between your windows and change the size of these. There is a minimum size required for each window, and if you go far past that, you can collapse it entirely, so that way if you want to focus on a panel and maximize it, you can do so, and then just drag it back out. So that's the overview of the NUSTool interface. Oh, I guess I didn't mention down below, sorry, this is where the plots will end up. So when we generate sample schedules, we'll be able to see them here, and we'll look at point spread functions in that tab. That'll be obvious in just a second. So now let's talk about parameter entry. So some of the parameters that we use when generating non-uniformly sampled schedules are parameters that we have to enter values, one for each of our indirect dimensions. So you can see here we're working on 2 indirect dimensions, and the number of points is showing us that we need to enter 2 integers, a value for each of those indirect dimensions. So this is a parameter that we refer to as matched, and you're going to get this placeholder text that gives you a hint as to what you're supposed to enter there. There are going to be other parameter entries like this seed value down below. It's just a single value. Doesn't matter how many indirect dimensions you have, it's just a single value. So keep that in mind as you navigate through this form. The next item I'll point out in the user interface, as mentioned here in the tutorial, is these info clicks. So you can see that the labels for these various fields are links and they're colored. If you click on them, you'll get some information about what that particular parameter is and what's expected there. I've already mentioned the sliders for rescaling the size of these different frames. So now what we'll do is just a very quick overview of the different modes that are available through NUSTool. Take a look at these tabs that are available up here. And after we step through all those modes, then we'll get our hands a little bit more busy and we'll start to generate some sample schedules and take a look at how the features of NUSTool operate. So we'll start here with the Generate tab, and we start in this dimensionality box at the top. This is where we really define the kind of geometry of our sample space, so to speak. How many indirect dimensions are we going to have? What's the maximum increment along each of those dimensions? And then we can define here whether or not we want our FIDs to be 0-based in their indexing or 1-based in their indexing. And this selection right here is just for how our sample schedules get visualized for us in this frame. When we go to write sample schedules to file, you can choose a different indexing for how you write it to file depending upon what instrumentation you're going to be using that sample schedule on. I'll also mention that for the duration of this tutorial and for today, just leave component sampling on full. This is kind of an advanced technique, something that we use in our own research in-house. It's not necessarily something you're going to be able to collect an experiment for or do the full processing on your own. But if you are curious, I do address this in some other presentations for the NMR Box workshop series, but I'm not going to get into that today. Then in the parameter selection down here, the first question you'll be asked is to pick what kind of sample schedule you want to generate. And once you pick one of those, it'll expand out and show the additional options that you can fill for that particular sampling scheme. And you can see the placeholder values telling you what kind of inputs are expected. You've got check boxes for Booleans where you can enable or disable a feature. Then we'll move on to page 4 here in the tutorial, and we'll go over to the write panel. So after you've generated a sample schedule, you can go in here and enter a path to where you'd like to write it to file. If you click on the select output file, you'll get a file browser inside NMR Box where you can browse through your file system and pick a location and pick a file. And as I mentioned before, this is where you can select if you're going to have a 0-based or 1-based sample schedule. And if you click on that for more information, you'll get some output there. If you have a sample schedule that was generated somewhere else, you can use this load panel, or you can give a path to that sample schedule. You can declare whether or not that was a 0-based or 1-based schedule. Again, leave it on full component unless you know otherwise, and you can load that sample schedule in. After you load it in, NUSTool will report to you here the maximum increment that was observed along each of your indirect dimensions. If you didn't sample out to your maximum increment and you know that those values should be larger, you can manually edit them and click this adjust button here, and then you can plot that sample schedule and you'll see what you've read in. Next, we'll move on to the Analyze tab. So this is a completely new feature for NUSTool. And now we've got some basic metrics that are available here. So after you've generated a sample schedule or read one in by file, you can come in here and we have a relative sensitivity metric. So if you declare the decay rate of your signal envelope and the sweep width of your space, you can then compute what percentage of that signal envelope you're capturing with your particular sample schedule. And this is something that'll help you get a sense for the sensitivity of your particular sampling scheme. Then we have a metric for mean evolution time, and this is simply going to show you the mean evolution time of each of the FIDs in your sample space. And that gives you a sense of the strength of the bias in your sampling. So if your mean evolution time is at smaller numbers, that means you have a very strong bias pushing you towards shorter evolution times. Comparatively, if your mean evolution time increases, you're now using a weaker bias that allows longer evolution times to be collected. And in this final section over here, we're able to compute point spread functions, plot them as 1D or 2D figures, and then we can compute the peak to side lobe ratio down over here. So that's the quick overview of kind of what's in here and where everything lies. Now we're going to move on to page 5 in the tutorial, and we're going to do some hands-on work here and start to generate some sample schedules. So in this next section, We're going to use 2 indirect dimensions. So go ahead to your Generate tab, and by default, that should already be on 2, but if you've changed it, go ahead and put it back to 2. And for component sampling, as I mentioned before, we're going to leave that on full. And for the seed value down here at the bottom, I'm just going to leave that on 1. If you want to leave it on 1, then you should see exactly the same sample schedule on screen that I generate. But in practice, of course, you can change up that random seed value. So the first sampling scheme we're going to take a look at is exponentially biased. So here in the parameter section, click on exponential. And then we have some basic information here in the tutorial about what an exponentially biased sampling schedule is going to follow. So here's a quick relationship up here that shows us how the decay rate of our signal envelope relates to the spectral width, which relates to our maximum increment, and finally the percentage of the signal envelope that remains when we get all the way out here to our maximum increment time. So what this shows us is that an evolution time of 0, we call that full intensity. And then depending upon what maximum evolution you want to look at and how strong your signal envelope decays, how quickly it decays based on this R2 value, we get this signal envelope that comes down and reaches a percentage of P at a maximum increment of M. So what we're going to do now, as we move on to page 6, is we're going to generate a sample schedule that's going to have 128 points on the first indirect dimension and 64 points on the second. So in number of points in that field, enter 128, a space, and then 64. For our coverage, we're going to put in 25% coverage, so you can just enter 25, and by default, this pull down is on percent. You can also put it on count if you want to specify an exact number of FIDs. In our case, we're going to enter a decay rate of 175 hertz on the first indirect dimension, 56 on the second, and we'll use sweep width values of 9650 and 1525. So with all of those values in place, we've filled this full form. So down at the bottom, we can click the Generate button. And I am completely shocked. I'm terribly sorry. I am just going to close this for one quick second and relaunch that. I don't know what that glitch was. I'll have to look into that. I'm sorry. But there we go. We've generated our sample schedule. We get a quick feedback that shows us for each of our hypercomplex components. We have 2 indirect dimensions, so we have 4 hypercomplex components. We've selected 2,048 FIDs, which corresponds to 25% coverage. We can now click on the plot button, and we'll see our sample schedule shown over here. And that's reproduced in the tutorial guide over here for those of you following along with that. So now let's go in and double our decay rate. So if we go into our decay rate field over here, we're going to double the strength of the bias, and we'll put in values of 350 and 112. And now when we generate that and click plot again, you'll see our sampling get shifted towards these lower evolution times. So we're constraining those points to be pushed towards those lower evolution times. So when people talk about having a matched bias or a double matched bias, this is exactly what they're talking about. In this first case, we matched our sampling to the R2 value for these parameters that we showed up here. And this would be typical for C13 and N15. And in this case, we've now doubled those decay rates. And there's a lot of evidence in the literature that sampling with a stronger bias than matched is advantageous. So this is one way to build such a schedule. So now we're going to switch up and take a look at quantile sampling. So go into this parameters box here, and under sampling scheme, we will select quantile. and you'll see a variety of parameters that now become available to you. Those are described over here in the sampling guide. But for now, I'm going to walk you into generating one of these schedules, and we'll start to learn about these parameters as we go. So let's change the number of points at the top here to 64 and 32. Then in our quantile section, we're going to leave the PDF on sign. So the probability density function, this is the shape of the function that's going to bias the distribution of our FIDs. In this case, we're going to use the sign function for quantile sampling. We'll leave the bias on 1. That's another adjustable parameter for tuning that strength of that bias. And then for bins, we're going to put in 16 and 8. This is what controls the coverage of a quantile sample schedule. We're going to end up chopping our sampling space into a grid that's 16 by 8, and we're going to sample 1 point in each of those bins. And the way quantile sampling defines those bins is it does so that each bin has an equal area underneath the signal envelope. So that way at the lowest evolution times, our bins are more closely spaced because we have large signal intensity there. And at longer evolution times, the bins start to cover a greater number of time points in our grid. In the evolution box, we're going to sample out to 3 times T2 along both dimensions, so put in 3 space 3. For jitter, we're going to put in 0.01. We'll come back to that in a minute. And we can leave these checkboxes all in the off position. So let's click on the generate button, and you'll see that we've created our sample schedule. Here's the output, and it shows 104 FIDs being collected, 5% coverage. So now we can go over here and click on plot, and we see our sample schedule. In the tutorial, I've got some guiding questions to kind of help you through looking at this. So why are the points in this sample schedule along these clearly defined rows and columns? Well, as I just told you, quantile sampling uses these bins, and each of these points has been put pretty much in the center of each of those bins. So we start to see the points line up on rows and columns. Is this bad? Well, yes, if we have regular spacing in our sampling, we're going to induce sampling artifacts. We've essentially created a frequency signature in our data set just by where we're sampling. So to confirm that, we can take a look at the point spread function. So let's go over to the Analyze tab. And down here, we're going to click on Compute Point Spread Function. We can click on 2D for our plot. And we're going to leave F1 on the x-axis, and we'll assign F2 to the y-axis. And we can click on Plot RPSF. And this is what we get. There are plus and minus buttons in here to adjust the contour levels. So if we start to descend down into that point spread function, we can start to see some pretty strong artifacts that are coming up along the ridges. We've got these uniformly spaced artifacts, and these are a result of our uniformly spaced sample points in our schedule. So the question is, how can we fix this? So let's go back to our Generate tab, and this jitter parameter is going to allow us to introduce some randomization where our sample points show up. So what we're going to do is set that to a value of 0.7. So that's going to give 70% of each quantile bin of its height, and 70% of its width is now going to be available for the location of that bin's FID. So when we go and generate that sample schedule and show a plot, you'll see that our points have now deviated from those perfectly structured rows and columns that we saw before. And of course, if we go into the Analyze panel and recompute the point spread function and plot that and take a look, we can descend down into our point spread function again, and you'll see that those ridge artifacts are less prominent and certainly don't exist in the same way that they were before. So now the next question over here, what is the percentage coverage in that resulting schedule? Well, if you take a look in the output that we saw in this window, you'll see that we're getting 5.18% coverage, which is not the 0.25% that we asked for, 16 times 8 out of 64 times 32. So what happened?
Hey, Adam?
Yes.
Sorry, is it okay to just ask question in between?
Yeah, if you have a question, go ahead.
Okay, the quick question, of course. The point spread function you show and then the one I computed on my box, after the jitter you increase, you see few still like noise spots there. Mine looks pretty clean. I'm just exactly typing the numbers. So is it like a scaling of the plot on the screen or?
Yes, it's going to be the use of these contour level buttons to go up and down. This is one thing I want to tidy up in the next version of NusTool. I'd like to have a slider here that shows you the threshold values that you're selecting for your contour plots.
Oh,
right
okay.
now, that's something that's kind of internal to the program, but I'll make that more transparent in the next version.
Okay, so it's kind of okay if it's slightly different from what you show and what I have on my box.
Yeah, exactly. As you descend through these contour levels, eventually you'll get all the way down into the noise and you'll start to see things down in the point spread function. And if you're way up high, you're going to clip just the peak of that
Right.
zero frequency component.
Okay, but where is that control by chance? That contour level, where do you?
There's a label in here that says adjust contour levels, and you have a plus and minus button right above the plot PSF button. That you should see on screen.
Okay. Thank you so much.
You're welcome.
Okay.
Sure.
Yep.
So as I was mentioning here, we ended up with 5% or so sampling coverage, even though it would appear that based on the number of bins we asked for, it should have been higher. So why does that happen? And as those quantile bins get spaced a little bit more tightly, it becomes harder to fit the selected number of sample points into those bins. So David Rovniak has a backfill feature. If you put that on and generate your sample schedule and plot, you'll see that all of those redundant points that didn't fit before are now backfilled at these low evolution times. So just keep that in mind. And of course, you can click on these tabs over here to see information about those particular parameters. And they're all documented here in the tutorial, even if I go a little quicker now. So once we put in the backfill and we go in here and compute our point spread function and take a look, what you're going to start to see is we now have some distortions that are appearing around the base of our central component along those ridges. And that's in part because with the backfill in, we've created this harsh transition. It's almost equivalent to having a truncation artifact in here. So one of the ways we can address that is we can increase the size of our sample space and allow our sampling distribution to more gradually decay. So here I am on the bottom of page 10. And if we go back to our generate tab, and instead of putting our samples on a 64 by 32 grid, if we up this now to 128 by 64 and leave all of the other parameters the same, and we generate our sample schedule, of course, our percentage goes down, but the total number of FIDs we're collecting is exactly the same, so our experiment time hasn't changed. And now when we look at a plot here, we still have that cluster down below, but we're using a larger sample space to allow our points to decay out over that. And if we take a look at the resulting point spread function, going to the Analyze tab and computing the point spread function, you'll see that some of those ridge artifacts that were right on that central component have changed. We've got a couple other little dots that show up on the vertical, but not nearly the same level of distortion right on that zero frequency peak. So hopefully kind of walking through quantile sampling here as a test case gives you a feel for how to generate a sample schedule in NusTool, how to visually look at that sample schedule, look at the point spread function that results, and be able to evaluate some of the properties that you might expect to see in a resulting experiment. I've got one other sample schedule that we can mention here because Poisson gap sampling is obviously very common in the community, and I'll just note that that's now a new feature in NusTool. So under the sampling scheme pull down, you're able to go in here and select Poisson gap sampling, and this will construct the parameter set you need to generate those schedules. There's one or two other items I don't have in my tutorial that I do want to touch on for today, just so you're prepared for the sessions that come in the afternoon. So as you go through and generate one of these sample schedules, and we were just in the quantile sampling and we generate a schedule, we get our feedback here. We can click this show command button, and this is going to show you the command that you can run inside NMR Box from the terminal, or in any shell script you write inside NMR Box that will generate the equivalent sample schedule. So that's why I mentioned at the beginning of this session, start with nustool in the GUI. You can learn the different parameters and features that are available in the different sampling schemes. You can play around with generating different sample schedules and using the analysis metrics to see what you get. And once you're happy with the sample schedule, we can write it to file, which I'll show you in just a second. And then you can capture exactly the parameter combination that was used to generate that sample schedule by either copying this command out and putting that into your own script, or documenting those parameters on your own. So here's the sample schedule that we have. And since we're going to be doing some NUS reconstructions this afternoon, the last thing I'll show you here is over into the right tab. We can select an output file. In this case, I'll go into my home folder, and I'm going to put out a file called schedule.txt, and I'm going to save it to that location and click the write button, and it tells me that the schedule has been written to file. If I slide nustool over and open up my home folder, oh, appears we have a slight delay with that. Well, when that home folder opens, there will be a file in there that you can see, schedule.txt. You can, oh, here we go. And we'll double click on that to open our text file. And you can see that here we have our FIDs. Now ignore, in this text editor, I've got row numbers that are being shown in the margin. That's not part of the sample schedule. So you see 2 time values in each row corresponding to the T1 and T2 indirect evolution times for the sample schedule. And as we defined here in nustool, we wrote this out as a 0-based indexed file. And that's why you see our values with a low of 0 up to a high of 63 on this first dimension. So later, when you do your reconstructions with Frank, you'll be able to use nustool to generate sample schedules. You can pick an output directory where Frank may direct you, and you can continually change your sample schedule, overwrite a nuslist file, and then include that in the reconstruction workflow that Frank shares with you. So that's it for my tutorial. I've got some future work that's annotated here in the bottom of that guide. And as I mentioned all the way back up here at the top, if you have any questions or comments, please email me at any time. And of course, you can put some notes in that box note that we're all sharing today. So with that, I will take any questions if we have them.
Hi, Adam. I
Yes.
have a question. So this schedule file .text, which you said, basically, if I use it in Bruker machine, this is what will replace the place of NUS list, correct?
Exactly.
In fact, I have to copy it over the same name, I guess. Oh, no, not necessary. I can actually type in the actual name in the.
The latest version of Topspin apparently now supports, you can now indicate a separate file.
Yeah, with the name, actual name. Okay.